on this computer. All right. Yes, I can. Why can't I minimize Zoom? Just watch me. What in the world? Okay. So what I'm going to do, because, all right. So share screen, whiteboard. All right, I'd like to discuss problem 3 on your assignment, which I know I've given some, I've helped some people fix the answer for that. But I figured it's worthwhile to go through it with the entirety of the class. So let's get cracking on this. Okay, problem 3 was asking for what the big O runtime of 1 + 2 + 3 all the way up to plus n - 1 plus n is. Okay. And if you look up the sequence in Google by typing +1, 1 + 2 + 3, you know, depending on where you stop, you might see something like this: 1 + 2 + 3 ... is equal to -1/12, which you should look up the YouTube videos on because it's a fascinating deep dive into crazinesses of mathematics. But if you continued on and it was like 1, 2, 3 ... plus n - 1 plus n, you'd probably find a Wikipedia page for triangular numbers. This sequence is triangular numbers. You might recognize it from Calc 2 if you've taken it as a converging series. In other words, and that means that basically it's some series of numbers, some formula that we know converges to a point. Okay, to some, so that we can give it some formula. And that formula is n times n - 1. Sorry, no, n times n + 1 over 2. Which, if you think about that, that's slightly more than half the area of a square. That's n by n, right? We've got an n by n square, right? And the first operation is this: first dot, then 2, then 3, and 4, and see how we've created basically something that takes up a bit more than half the square, right? But let's go ahead and solve that mathematically. I know this because I feel like you can get all the use out of proof by induction you can. So proof by induction is a way of proving something, but with 2 rules. The first rule is figure out a base case. In other words, we've got this formula, +2 + 3 plus n is equal to n plus 1, n times n + 1 over 2. So we've got this formula, figure out some number for which this works. Okay, some base number as small as we can get. Well, let's let n equal 1. So that would be 1 all the way up to n, which is 1. It's equal to, and now we just plug in n, right? 1 times 1 + 1 over 2, which that comes down to 2, which these 2's cancel, which makes this 1 equal to 1. Ta-da! Okay, like, right, no great surprise there. Okay, the math here is pretty easy. I like easy math. It's part of the reason why on math exams that the answers are so often 0, 1/2, or 1, or a negative equivalent of those, because the math works out nice and easy and it's easy to check the answer. Your math professors are just as lazy as you, trust me. So, or perhaps they're just as lazy as me. But anyway, so that's the first part. So we've proved a base case, which we've proved that formula is true for n by n is equal to 1 because we solved it. You know, we did actually work through the steps of solving it. So the next thing is assume true for k. Assume it's true for some k, and then prove if it's true for k, then it's true for k + 1. So what this means is that essentially we want to show that if it's true for 1, then it's going to be true for 2. And if it's true for 2, it's going to be true for 3. If it's true for 3, it's going to be true for 4. Does that make sense? So except instead of proving each of these things individually, I'm just going to prove it for generic k and show that if we assume k is true, then k plus 1 is true. And what that allows us to do, well, is to say, well, 1 is true, so that 2 is true because 1 is true, and 3 is true because 2 is true, and 4 is true because 3 is true, and so on and so forth. So basically, by proving this generic case, we can show that because we have a base case, that base case acts like a domino and knocks everything down and makes it true. So we assume that if it's true, that we assume that it's true for k. That means that it's going to be k. So we're going to try to prove it for k plus 1. So that just basically means that we substitute n with k plus 1 everywhere in the formula. 1 plus 2 plus 3, ... plus. Now, instead of n minus 1, I'm going to do k because the next number is k plus 1 because we substitute an n for k. Make sense? Or n for k plus 1. Okay, now the next thing we do is set it equal to the formula, which was n times n plus 1 over 2. So that was k. Right, everywhere where I see a k, I'm going to just do k plus 1 instead of an n. Now here's the trick for solving induction. Don't change your right-hand side as much as you can, okay? Don't change it if you can. Now for the left side, how in the world do we get to this if we're not supposed to change the right-hand side? Well, the trick is that first part of this proof, which is that we assume it's true for k. Well, and what does that mean? Well, we know what this is, right? We said we assume it's true for k. We assume this works for k. So this sequence, 1 plus 2 plus 3 plus 4, all the way up to k, we can turn that into the formula that we are assuming that is true for, which is, so we can change this into k times k plus 1 over 2. All right, that's the original formula, just with n replaced by k, because we assume that that's true. Plus this k plus 1 hanging out by himself. Right? Now you note that that we've got a 2 down here. We've got a single fraction, so let's fix that. What I'm going to do is I'm just going to multiply this entire thing by 2 over here, right? That makes sense? I'm just multiplying that thing by 2. So, or I'm putting it over 2 rather. I'm multiplying it by 1 so that I can get it. I multiply by 2 over 2 is the point. So now because that's that, I can put it all over a single denominator. Yeah, okay, there we go. And so now we're left with this, which looks unusual because when you're like, well, okay, where can I go with that? Well, you got to switch your focus because normally, which is basically we've got this common k plus 1 factor. And normally when we factor something, it's like to the left of, it's on the left side of the things we're factoring. So that can throw you for a loop. But we can factor out that k plus 1 over here. Right, if we factor out that k plus 1, then we end up with k plus 1, and we factor it out and we get k, right, plus 2 over 2. And if we note k, and if we look, that's the same as what we had on the right-hand side, which is this k plus 1 times k plus 1 plus 1, right? We just simply have to, we could just simply break this apart because addition is, because 2 is just 2 1s added together, as my 4-year-old is so delighted to tell me. So we've proven that those two things are equivalent. Now, I did that because proof by induction I find a pretty useful proof. It comes up a lot because, especially for computer scientists, because it helps us understand it helps get our mind ready for when we deal with recursion. Okay, because recursion, proving that something is recursive bears a lot of similarities because you've got a base case and you've got a recursive case. And you want to show that the recursive case always goes down to a base case. But this formula, this thing, which is to write it a bit easier, sum of I is equal to 1, right? This thing comes up in our algorithms a lot. So for instance, if you did your isUnique function where you were comparing every item to all the items that were to the right of that item, then that is that kind of sequence that you have: 1 plus 2 plus 3 plus 4 plus 5, so on and so forth. Except it was in reverse, and you weren't comparing it to itself. So technically it was, you were comparing one item to the n-1 other items, then another item to the n-2 other items, and then another item to the other n-3 items that it hadn't previously checked. And so on and so forth until you got to the last item, who was like, and I compare myself to myself, or not, depending on how you wrote it out. But the point being is that, like, that still kind of reduces to that n times n plus 1 over 2, just with a little bit of adjustment, but still a quadratic formula, right? That's still quite a big O quad. That's still big O of n squared because of that. For number 4, I would again look up, kind of see how that convergence how that converges. You might Google 1 squared plus 2 squared plus 3 squared and converge on that one and see how that works out. And because that also follows a formula. And you're probably thinking to yourself, okay, it's not n squared because number 3 was n squared. So it wouldn't make sense for the ones that we're adding all the squares ones to be squared as well, which is a pretty good assumption on your part, which means that it's got to be n cubed or n to the 4th, right? Just kind of with a naive kind of level of thinking, which is like without any background knowledge, because like, okay, it was either going to be 1 above because we raised the power by 1, or because we squared it, it's got to be n to the 4th, right? It's got to be one of those two. So it's your job to figure out which one that is. Or rather, it was some other mathematician's job to find out what that was, and it's your job to figure out what his solution to that was. So any questions before I let you get to work? All right. Another, just again, administrative stuff here. It is too late to get the Moderna vaccine, I believe, right? At this point, I don't know what the count, I haven't checked the countdown page. I can pull that up if you want me to. People want me to pull that up? Right? If you haven't gotten your vaccine yet, first off, the vaccine is pretty awesome in the fact that it really helps you not die of COVID, which is like kind of the benefit of there. In a computer science related thing, I just want to talk about, so you've got to get it pretty much tomorrow, Pfizer, if you're going to get it. Otherwise, you got to get the Johnson & Johnson if you're not yet vaccinated. I just want to talk about for a second, just kind of how awesome the amount of just scientific resources we threw at, and I say we as humanity threw at this problem. Exascale computing, folding at home. How many of you know about folding at home? So folding at home, and I'll share my screen so that this will get recorded on the screen. Okay, folding at home started out as a project like a while ago to basically say, let's distribute, we have these protein folding problems, which is simulating the way proteins move, that are resource intensive. If we had a lot more computers, we'd be able to solve this a bit better. So the way, and this was years and years ago that came up. So the idea is you run, it's kind of a donationware. Except you're not donating money, you're donating your computing resources. You download it, install it on your computer, and it runs in the background and uses your, when you're not busy, and uses your unused computer resources. If you've got a powerful graphics card, it can use that too, if you let it. just don't try to game at the same time as doing it, because it's doing some number crunching on your graphics card. So with COVID-19, it did some, that started up and did some simulations. But the big thing is that SARS-CoV-2 simulations go exascale to capture spike opening. This is the first, because of the amount of people that basically donated their computing power to this project. It was the first kind of exascale computer. And if you think about that, that's giga, tera, petascale, exascale. So the amount of computational kind of operations that were going on to deal with that. It was insane, the amount of power that was going on. This is the growth of the of folding at home users as for the COVID-19 cases last year, and just how many people. You can see here that there was a huge spike after it was declared a pandemic for the number of people who started doing folding at home, and the number of people. So here in Project C, though, these are the processing speed and exaflops. This is a way, which is a really weird way. It's, floating point operations per second, which is a weird way of measuring computing power, but it's the standard right now. These are all different kind of computing. These are different computing resources or different computers or supercomputers and supercomputer formats have been built. And here's where they all are. And here's where folding at home got to during the COVID-19 pandemic, which is, again, it's a distributed computation, which is just works on it. And it is all about, so a ton of research was just mustered on this. I know this really doesn't necessarily have anything to do with, in any way, convincing anybody about vaccinations or anything like that. What it should show you, though, is that humanity has dedicated a lot of resources to this. And if you still want to help, it's not too late to help. You can always run. You can still download and run this. Yes.
How does it separate the work on each computer?
It gives you a couple of simulations and it sends it to you over the internet, and then your computer, once you're done, sends it back. If it doesn't send it back in a time frame, it sends it back to it marks that as lost, and then sends it to another computer. It's basically distributed workload. You have certain tasks, and I don't know precisely how it works, but maybe you'll say, try these simulations with these random numbers or these parameters. You try these simulations with these parameters, because they're all computationally expensive. And brute forcing it is like the only way to do it. But what's cool is that there is a lot of computational resources going on, and there are still things you can do as to help. Although I would suggest maybe waiting till winter to do that when it gets cold, if you've got a laptop, because at least that way you can use a laptop as a heating source. Because again, you can run it on your laptop. Just be sure that's going to be sipping your energy and not chugging it. That's all I'm saying, is that if you want to do these kind of heavy end computations, the laptops are not meant for that. And laptops are meant, the way modern laptops are made for are for bursts of processing power, not necessarily going full steam ahead at all times, because they just don't have the cooling for that. All right, so that's what I've got for you today. I'm going to start recording.